All right, guys, we are taking a look at our intro to equilibrium and reversible reactions. So follow along on your fill in the blank notes. In this, we will explain the reversible chemical and physical processes and how equilibrium is established. We will also represent a system undergoing a reversible reaction with a particulate model or a particle model. So what's a reversible reaction? Most reactions we've seen have been one directional. Some reactions can only occur one way, like combustion. We can't unburn a fuel. You can't unburn a piece of paper. It only goes one direction. But many reactions can be reversed, meaning that the products can turn back into the reactants. So for example, hydrogen and oxygen gas can react to form water, and water can be split apart into hydrogen and oxygen. Now, that process, that reversible process, doesn't occur without considerable energy being added. So the reaction will not just reverse because there's activation energy needed for both the forward and reverse reaction. So if we look at this graph here, we've got our activation energy for our forward reaction going from left to right. So hydrogen and oxygen making water. That's a considerable amount of activation energy. But if we reversed it and went the other way and took water and made it back into hydrogen and oxygen gas, that is an even higher activation energy. Okay, so it's not just going to always happen on its own, but when we have a reaction where this hill is not so dramatic, we have the products and reactants have lower activation energies, it's much easier to be reversible. So when a reaction is reversible, both the forward and reverse reactions occur simultaneously at the same time. So a good example would be hydrogen and iodine making hydrogen iodide or hydroiodic acid. The initial direction depends on the amount of chemicals in the container. So for example, if we look at this first graph here, so let's call this graph number 1. So if hydrogen and iodine are in the container to begin, so I take a container, it's empty, it has no chemicals, and we add hydrogen and iodine gas, those would be in high concentration. So we can see that their concentration starts out really high, and the forward reaction will occur at a faster rate. Okay, so at a faster rate. We're going to start out with just the reaction going from reactants to products, going in the forward direction. Some of the products are formed, or once some of the products are formed, the reverse reaction can start to occur. The reverse reaction will speed up as more products are formed. So as we start to form products, our concentration of products is going to slowly increase, but we're also going to have some of that product turned back into the reactants. So both reactions, forward and reverse, occur, and they continue until the rate, so the speed of the forward reaction and the speed of the reverse reaction, or rate, are equal. So where rate forward and rate reverse are equal. This is when we establish equilibrium. Excuse me. So we can't really see the rate very easily on these graphs, but they are there. The rate is the change in concentration over the time, which is essentially the slope. So we can see that eventually the slope of our lines becomes horizontal, and they both reach a point where they are both the same rate, right? They're both horizontal, so they both have the same slope of their line. At that point, we can see where equilibrium, that dotted red line, has been established. That's where they both start to become horizontal, and that's where our equilibrium has occurred. Now, when we look at that for the first graph, hydrogen and iodine, H2 and I2, have a low concentration, while HI has a high concentration. Now you'll notice that H2 and I2, they're not used up. Their concentration isn't at 0, there's still some there, but there's much more HI in the container at equilibrium. So it's favoring the products. We're making more product here. Now if we look at the second graph, let's call this number 2. So graph 2 shows what happens when HI is in the container to begin. So a little bit different situation. So instead of, we start with an empty container and we put HI in there. Okay, so we're putting product in there. Well, that means that our reverse reaction is going to start out fast. So the reverse reaction occurs first. We're going to use up some of that HI and we're going to make some of that H2 and I2. Those are going to increase as more reactants are formed. Now, no matter which chemical we start with, they both reach equilibrium. We can see that the second reaction, graph 2, still reaches that horizontal line. So that same slope for both lines, that's when they've reached equilibrium. And that the ratio of reactants and products is the same. So we have about the same amount of reactants and products when we reach equilibrium. So those are the things that occur to establish equilibrium. The reaction starts, either the forward or reverse reaction is going faster at first until the forward and reverse reaction reach the same rate, the same speed, and that is when we reach equilibrium. We can see in both of these that HI is, we produce more of that chemical than the H2 and I2. And so it's favoring making products, but we don't use up all the reactants. We still have some reactants there. So we create this balance point where we're going to have more of one chemical than another, more reactants or more products, and we reach our equilibrium. Okay, so let's talk a little bit more about that. All right, so what are reversible processes? So any change in the state of matter, so solid melting into a liquid, liquid boiling into a gas, or the reverse of that, a gas condensing to a liquid, or a liquid freezing into a solid, all of those are reversible processes. We can change between them very easily by adding or taking away heat. Another example is dissolving. As we saw in our last unit with solutions, we can dissolve a solid into a solution. So you'll see S and then the arrow with AQ. That represents a solid forming an aqueous solution. So you can see over on the right, it's defined. You should add that to your notes. Aqueous just means it's dissolved in water. Okay, so all the solutions we were looking at in the last unit were all dissolved in water. They're all aqueous. So if we dissolve something in water, that's reversible because we can evaporate the water and form the solid again. So that's reversible. We also call that process the precipitation of a solid. So because the solid kind of falls out or sinks to the bottom. So that's precipitation. So that's the aqueous solution forming the solid or crystallizing that solid. So that process is definitely reversible depending on if we're adding water to dissolve it or taking away water to precipitate it. Some other ones that we get more into when you get to higher levels of chemistry are acid-base reactions, which basically are the transfer of hydrogen ions, which we call protons, or the transfer of electrons during what are called redox reactions, which is basically when we transfer those electrons to create like ionic compounds or do combustion, things like that. So those so the transfer of electrons in a regular redox reaction is a reversible process. Actually, a really good example of a redox reaction, it's also called oxidation reduction, is basically a battery. So if you think about your battery in your phone, you use it and that's going through one chemical process, and then you charge it and it reverses that process, so then you can use it again. So that's an example of a reversible process. All right, so what does equilibrium look like? So we have the microscopic view, and we're going to talk about these little GIFs at the bottom in just a second. So microscopic, if we could zoom in on the actual particles, we have what's called dynamic equilibrium. And that occurs where we continuously see reactants forming products and products forming into our reactants, and they occur at the same rate. And this occurs in what we call a closed system. So you can see in that first picture down there, we've got this zoomed in view of our little fish. So ignore the K part, we're going to get to that later. But it has 10 fish on one side, and then fish swim to the other side, and it eventually reaches a point where there's 5 on each side. And that's the equilibrium that's established. No matter what, if a fish swims from one side to the other, they're always going to equal out at 5 on both sides. Now, in the other picture, we can see there's a cat there. So the cat is scaring off the little fish. So in this one, we reach an equilibrium where only one fish occurs on the left side and 9 stay on the right side. So that's our new equilibrium. So we're seeing that the amount of chemical or amount of fish in this case is not changing over time. So the amount of fish going from the left side to the right side is the same as the amount of fish going from the right side to the left side. One of them is exchanging back and forth, so it's occurring at the same rate. So the amount of chemicals, the concentration of chemical, or fish in this case, does not change. We have reached an equilibrium. Both of these, the one on the left where there's 5 on each side and the one on the right where there's 1 and 9, are both at equilibrium. They reach a point where the amount of fish is not changing on each side. They don't have to be equal amounts though. So if we could zoom in on a chemical reaction, we're going to see this very dynamic process. We're going to see this colliding of molecules, these reactants forming products forming reactants, all of this occurring, and it's very robust and active. But if we zoom out and we look at the macroscopic view, it looks like nothing's happening because our overall amounts of chemicals aren't changing. We can see reactions more when there is something changing, right? When an amount of chemical is changing. So essentially our molarity of our chemicals is constant and thus at equilibrium. So if we do our reaction and we reach a point where maybe there's 2 molar product and 3 molar reactant. Say there's a color for one of those chemicals. Eventually, we're going to see that color change until it reaches equilibrium, and then we're not going to see any more color change. It's going to look like nothing's happening anymore. So microscopically, it's very dynamic. It's very active. There's all kinds of things happening. But in the macroscopic view, what our eyeballs can see, it looks kind of boring. It looks like it stops, but it just reaches that equilibrium point. Now, the biggest thing, the biggest misconception of students and of people out there is equilibrium means equal amounts, equal molarity, and that is simply not true. We are going to see situations where equilibrium means we have more product and a little bit of reactant. We're going to see situations where we have a lot of reactant and only a little bit of product is formed. And we will see situations where they balance out and they're about the same. So equilibrium means equal rate, not equal amount. And that is huge. So let's take a look at analyzing a couple more of these graphs, seeing what's going on, how can we determine what concentrations things are, and when they establish equilibrium. So our first question here, we've got a reaction N2O4 makes 2 NO2, so we're breaking a bond there and creating 2 different molecules. So it says, what is the initial concentration of N2O4? Well, our concentrations are on the y-axis, and they're times 10 to the negative 2. So whatever our concentration is there, we're going to move that decimal twice over. So our initial concentration would be at time 0. So for N2O4, that's our little boxes, so that's at 10. So 10 times 10 to the negative 2 would be 0.1 molar. And our initial concentration of NO2, we can see down here, is 0. All right, 0 molar. We start out with no NO2. So no product, we start with all reactant. And it says, what time is equilibrium established? So we're going to establish equilibrium when the lines flatten out, when they first flatten out. So it looks to me like that's right at 60 seconds. So that's a pretty fast reaction there. It only takes about 60 seconds for it to react until we get this balance point. And you'll notice the time keeps going and the amounts of chemicals stay constant. So to us, with our eyeballs, it won't look like anything's occurring. Excuse me. So what is the concentration of N2O4 at equilibrium? So that chemical drops down to a concentration, we can see, of 4. So it'd be 0.04, so times 10 to the negative 2 in this case. And NO2 has increased. We've made more of that, and we have now 12, so 0.12 molar. Oops, sorry for my terrible writing here. 0.12 molar. So the rate of the blank reaction increases over time. So the one that is increasing over time is our rate of our our reverse reaction, right? Because we are slowly, it is hard to write with this. We are slowly taking our product, making our product, and then we start with no product forming back into reactants, no reverse reaction because we have no product. And over time, that's going to increase as we make more of that product. It's able to form back into the reactants. And the rate of the forward reaction, let's see if I can write this better. Ooh, terrible. All right, the forward reaction decreases over time. So we start with a really strong forward reaction, and then over time, it reaches a point where it's the same speed as the reverse reaction. It slows down as we use up some of that reactant. So when the rates are equal, the reaction is at equilibrium. Okay, when they're equal, it's at equilibrium. So that's when we hit that 60-second mark. So why does the amount of NO2 increase more than the amount of N2O4 decreases? So that's an interesting one. We can see that our N2O4 went from 0.10 and dropped to 0.04. So it lost 0.06. Okay, and our other one went from 0 to 0.12. So it gained 0.12. It gained twice as much as the other one lost. Well, why would that be? Well, we can look at our balanced reaction. For every one N2O4 that we react, we're making 2 NO2s. So we're going to make twice as much of that. So it's because of our balanced reaction, our mole ratio. So NO2 increases at twice the rate that N2O4 decreases because it has that coefficient of 2. We're making 2 of those every time we react one of the reactant. So that's why we get that doubling of the rate or of the concentration. All right, so let's take a look at another one. Maybe stop, pause this, and try this one out on your own. Come back and I'll go over it. All right, so looking at this, it says the reaction container initially contains it only contains SO3, so it only contains our product. How do we know when equilibrium has been reached? We know it's been reached when the rates of the forward and reverse reaction are equal. All right, so that's where we hit that time. We can see that dotted line drawn there. So why does the amount of SO2 increase more than the amount of O2? So those are both reactants. We're reversing the reaction a lot to start with. Why are we making more SO2? Well, we can see based on our coefficients that for every 1 oxygen we make, we're going to make 2 SO2s. So that's why we get that increase of SO2 more than O2. It's about twice as much. And you can see that on the graph too. The amount of O2 and SO2 that we get to at equilibrium is about twice as much, right? If you divided this up, you're doubling it. All right, so the rate of the blank reaction increases over time. So the rate of the forward reaction in this case is increasing over time. As we make the SO2 and the O2, we can start increasing the rate of the forward reaction. And the rate of the reverse reaction is going to decrease over time as we use up that SO3. When the rates are equal, the reaction is at equilibrium. All right. Okay, so let's take a look at one more, I believe, one more part. So the direction of reactions, a couple of things. When the rate of the forward is greater than the rate of the reverse. So when that forward reaction is happening more or faster than the rate of the reverse, then more reactants are turning into products and more products are forming, okay? When the rate of the reverse reaction is greater than the forward, more products are turning into reactants, so more reactants are forming, Okay, so that can help us if we can look at something and see which one's creating more at that time, we can know which reaction is being favored, forward or reverse. So let's take a look at this picture. This is a great diagram to show us what's going on as well. So which reaction initially occurs at a faster rate, the forward or the reverse? So looking at our picture here, we've got chemical X and chemical Y and then chemical XY. In the first box here, we have only X and Y. So the only reaction that can occur right now is the forward reaction. We can take X and Y and make that compound XY. So that occurs at a faster rate than the reverse. The reverse is happening at 0 rate right now. Now, at what time is equilibrium established? So when do we get a constant amount of chemicals? So we can see that first box, the second box, we get 2 of the XYs. On the third one, we have 3 of those XYs. The fourth box, we also have 3 XYs. And same thing in our fourth box. So it first starts to stay constant at 200 seconds. Okay, so the concentration of blank increased over time while the blank decreased over time. So the concentration of XY or our products increased over time while the reactants decreased over time. As we used up X and Y to make our product, those decreased, and the combination of them, the compound XY, increased over time. Now, what is the concentration of each chemical at equilibrium? So we start to hit equilibrium at 200 seconds, so we can just count our particles. So XY I already circled, we have 3 of those, we'll just say it's 3 molar. Remember, chemicals in brackets, and we're going to see this throughout the entire unit, chemicals placed in square brackets mean concentration or molarity of. X is the little black dot, so there's only 2 of those. And Y is our larger circle. We have 1, 2, 3, 4 of those. So those are concentrations at equilibrium. Notice they are not the same as each other. Rate is equal at equilibrium, not amount. So that gives us an idea of what reversible reactions are, how we establish equilibrium, and how we can analyze some graphs and pictures to get an initial idea of equilibrium. Thanks, guys.